Okay, so let's get going. For today, I'm going to have to apologize. It's going to be terse. We're not going to be talking a lot about physics, but what things are involved in trying to do the physics we kind of describe on the first day. I also want to go over the derivation of the row solver, just because what's involved, you'll see many of the discussions we have, and just also to kind of diffuse any possibility that this came out of the blue from no good reason. And then we're going to just do a little bit of recap, the kind of things we learned here, and how, in order to move to the case of relativistic hydrodynamics, the discussions we had prior to it will strongly influence the way we do things. Also, I want to point out a good, very useful reference. So there are many books in numerical relativity. There are many also books in the derivation or the implementation of hydrodynamics. So I described one, I mentioned one yesterday, Randy Levesque's book on theory and approximations to conservation law problems. But as we go and move into the type of issues that we need to deal with in general relativity, Miguel Cubier's book is actually very useful. There are 4 or 5 out there. I think the description, the introduction here is at the right level. So that would be one source. So first, let's go back to the Burgers equation and try to compute the shock speed. Remember, we assume we may have a case where we have a state at the left, a state at the right, and what we're interested in getting is how fast will this shock that we form, the shock front, propagate. And we saw movies yesterday of how this behaves. But I mentioned that there was an analytic solution, and we can find what it is. And we're going to use that later on in the derivation of the row solver. So again, suppose we consider this equation. Oops, sorry, you. So it's a conservation law. So we have the rate of change of some variable u given by some fluxes that depend on that variable u, the gradient of it equal to 0. And we say that one useful way to describe the situation is to take the integral of both time and space and then consider, like, we're describing cells and how the content of the variable u on average in that cell varies as fluxes come in and out of that cell. So we saw in the movie that this thing translates into something that begins to show kind of a behavior like so, and this is moving to the right. So we want to understand what is that speed of propagation. So now let me imagine I do the integral of dt dx of this whole thing. So this will be when I take this integral, I have d dt after integral between x1 and x2 of u. Let me just check. U dx plus the integral of f evaluated in x1, x2 equal to 0. So here I'm doing the integral of time. This is the flux in the t direction, and then we have the variation, well, the difference in the x1 and x2. Now let me split this integral and ask this integral to not go from x1 and x2. x1 is some point to the left, x2 is some point to the right. We're going to assume that the shock speed that is somewhere there is described, or the shock front is described by some function s of t. So I'm going to turn this integral into the integral between x1 and s of t plus the integral between s of t and x2. And we're taking the time derivative of that. So when we take the time derivative of that, we're going to have several terms. We're going to have a term that will know about the time derivative of the function that is determining the end of our interval. And then we're going to have whatever is left, which is the integral of the time derivative in here. So this will be given by, let's call u left s dot. So it's a value of the function at the left minus the value of the function at the right. And we have s dot because we have so to take into account the time derivative of the interval that is changing in time. And then we have the integral of x1 s u dx plus the integral of s x2 u dx. In the right-hand side, on the other hand, we just have the fluxes evaluated at the right and the left. So I'm just going to write this as f of u left minus f of u right. We're interested in exactly what's going on at the shock. So now I'm going to take the limit of x1 going to s from the left and x2 going to s from the right. So I'm just shrinking the interval to 0. So then these two go away in that limit, but we still have this contribution. So now what we have found is that s dot is equal to the flux at the left side of the interval minus the flux at the right side of the interval divided by u left minus u right. So far, this is for a rather generic equation. We haven't made any explicit call yet for the Burgers equation. We can take a look at what's going on for the Burgers equations in particular. But so far, as long as we're in one dimension, what we've done so far is general. But let's specialize now for the case where this function f happens to be 1/2 u squared. So if I replace this in here, I'm going to have 1/2 u squared left minus u squared right divided by ul minus ur. And now we can just use the identity and write this in terms of the product of the sum times the product of the difference. So this will give us, for s dot, simply 1/2 u left plus u right. So this is for Burger equation. So at least in simple enough cases, we can understand the speed of propagation of the shock. This was a case where we had the left value of the function be larger than the right value of the function, and both positive, everything is moving to the right. I also mentioned that if we have the opposite, we have the refraction waves. By a similar argument, one can also compute what is the speed of propagation of that fan that opens up. And this is something one can then go and check numerically if you're recovering. And the solutions yesterday show superpose the numerical solution with the analytical solution, and that was kind of something we're using to, to identify what method was doing things correctly. So now let me turn to the row solver. So yesterday I presented a few things. It went a bit too quickly. I just want to make sure we clarify that and where that solver come from. After we discuss the importance of solving the Riemann problem and thinking of a fluid as the fluid behavior as being described by a series of constant or a series of Riemann problems one next to each other. So what is it that we're picturing? So let me draw here. We imagine we have a solution which could be generic. So let me imagine we have some fluid that maybe is behaving like so. and maybe the shock front is moving to the right or to the left. We're also imagining that we have a grid. So the grid has some points or some discretized values that we introduce to turn an analytical problem into an algebraic problem. When we're thinking of finite differences, and these are things like I think you discussed or you saw with Sasha Husa, you were picturing the solutions as being described by the values that the function has at these grid points. So this is more or less what a finite difference approximation does for you. You change a continuous function into a sequence of discrete values at grid points, and then you try to reproduce or provide approximations to all the continuous derivatives you have in the problem, and once you put everything together, you turn the continuous problem into an algebraic problem, and that's something the computer can do well. In the fluid side, because we're concerned about things like this, where if we were to be taking derivatives by, for instance, taking that point and that point, or these 2 points to make a central derivative, we're going to have a huge gradient. And that gradient will introduce very strong oscillations, and we're going to be very bad at trying to reproduce these features with any reasonable grid, especially in the case where this might get steeper and steeper as time goes by. So this finite volume strategy changes this into saying, well, take any cell, and in that cell, picture the average of that cell, say. Same thing here, that would be the average. Maybe the average here would be like that. And so now our function will be pictured as a sequence of piecewise constant values in each of the cells. Once we have done that, then notice that each interface, let's consider for instance this one, we have the value of the function here being constant and the value of the function here being constant, but with a significant jump. Then we're back to a Riemann problem. We're back to a case where we think across an interface, which would be here, we have a left state of the field, a right side of the field, and then we need to solve this Riemann problem. The problem in practice is that to solve the full Riemann problem is complicated, it's expensive, and we also recognize that when we do this, the solution is actually better than what giving it credit for. So at least in here, where everything is rather smooth, we're still approximating things with a rather coarse approximation. We're just saying it's constant in that interval. So given that we're paying that price, so that's the price we're going to pay to try and deal with problems like this one. And since we're already paying the price of making some error, which is approximate, say first order approximate, so we might as well just introduce a first order approximation everywhere, just to kind of reduce a little bit the computational cost. And this is what these approximate Riemann solvers do, and the roll solver is an example of that. So let's just walk through the derivation of the Riemann solver, and then you'll see how everything we've been discussing in one way or another comes into play. So the idea of rows was to say the following. So we're dealing with a problem, again, oops, that may be like so. He will say, well, turn this problem into now a linear problem that depends on points. So it's a variable coefficient problem, which you're going to write at least formally like so. We're going to ask this problem to satisfy some key properties for it to be a good representation of the problem we really wanted to solve for in the first place. So A will have to satisfy some property. So let's call, say, 1. If F is the flux, say the flux at 2 points, say, across an interface, we're going to try to approximate it with this matrix A, which you still have to define, that may depend on both the values at each side of the interface times simply the difference between them. So of course, we can already see what we're going here with. So we're saying, formally, this, when I iterate on the cell, will give me the value of the flux at one of the cell side minus the value of the size of the other cell side. We're trying to reproduce these in this problem. We're going to change this F into an A, and then we want that A to satisfy precisely this relation. So if we're satisfying this problem now is capturing the solution of this problem. We also want some sense of continuity on a piece of the solution that is smooth. So if there is no difference between U and V, or they are getting approximately the same in some sense, then that should be reflected in the matrix A. And the third property is a property we've discussed again and again. So this should be diagonalizable. With real eigenvalues. And this we want, otherwise we know the problem will just blow up in our faces. But we're going to use that property quite extensively in the construction of the approximant. So let's take now an interface, whatever that is. Let's imagine that interface, the cell to the left of that interface is labeled I, and to the right of it is labeled I plus 1. So let's imagine that it's diagonalizable with real eigenvalues. Because it's diagonalizable, let's imagine that the eigenvectors associated to the eigenvalues to the right, let's call them RP, where P now labels all the eigenvectors or eigenvalues that we have. And the associated eigenvalues, let's call them lambda P. So with this matrix A, satisfy A times RP is lambda P. So it's a real eigenvector. So now let's decompose U at the ith side, or at the label I. We can always do the following. Just write it as a sum over some coefficients times our eigenvectors, right? Because we have a fully diagonalizable matrix, we have a set of eigenvectors that span our space. And so any function or any vector that we care about can be written in terms of the eigenvectors. This is all we're doing here. And let's say, similarly, I plus 1 is the sum of gamma p, rp. Now, let's take the following operation. Ui plus 1 minus ui, which we can do, is just simply the sum of gamma p minus beta p rp. And we're just, because it will come handy, let's call this the difference between gamma and beta. Let's give it a new name. So notice what this is beginning to say. So we decompose U, kind of the left side this way, U on the right side this way, and now when we take the difference, we're still using the right eigenvectors, and we have this thing where we're calling alpha. Alpha is measuring the jump. So if the solution is totally continuous, gamma and beta will be the same, and then this will be 0. Now let's imagine at this interface, we're trying to say what is going to determine the solution here. So if we were working on the transform basis, remember we said that one particular property that is particularly useful of this is that we can always think that there is a transformation into just a diagonal problem. And that diagonal problem is described by eigenvalues that are either positive, negative, or 0, and depending on the sign of that eigenvalue, we know if things are moving to the right or to the left. Right? So what we're going to say in the next step is, if I consider this cell, and what is determining the solution on this side, as a contribution from this cell, it's only that piece of the solution that is described by the eigenvalues that have the right sign that tell me this is information that moves to the right. Are we clear on that? And we're going to use the same thing on this side, except that now we're going to pick the other eigenvalues, the one that give me the sign that tell me that things are going from right to left. Just as a warning, in many of our discussions, we're working with this equation, and we were saying, oh, if lambda is positive, this is moving to the right. If lambda is negative, this is moving, if lambda is positive, it's moving to the left. If lambda is negative, it's moving to the right. But just to be maximally confusing, when we talk about the equations of motion in conservation form, the flux is here. So now this one is in the left-hand side, so we are going to have to change the signs. So just remember that. So now the solution of our Riemann problem, or at least this understanding that something is determined from the left onto the face and from the right onto the face, will be given by the following. So the sum of positive eigenvalues, BP, RP, so these are the contributions from the left side, plus the contributions from the right side, but they have the opposite eigenvalue signs. Right? This is all we're saying. Just pick from here what comes to the boundary, pick from here what comes to the boundary. And now your solution would be the combination of those two. But now we can just massage this a little bit for convenience sake, because we might find it more efficient to deal with something that is related to this. So let me rewrite this in the following way. So here I was adding only the eigenvalues that were graded only over a subspace where the eigenvalues are positive. So let me just relax that, add everything, all the eigenvalues for this piece, so the full UI, but subtract the piece that has the opposite sign. So I can write it this way. The sum over all lambda piece of BP, RP, plus the sum lambda p less than 0 right? The only thing I did is just add and subtract to this one the piece that has the opposite sign. We don't care about the signs that have eigenvalue 0, because in the end they're going to be multiplied by 0 and they don't contribute. So we can imagine we can include them or not, it won't change anything. So then this turns out to be UI plus the sum of the lambda p less than 0. And we already had a special name for gamma minus beta. That's alpha p RP. Now we can do exactly the same thing. And concentrate on this one, do the same on this other side, except we have to do the flip of the sign. So let me not draw this or not derive this, but you can convince yourself very quickly that this is true. Yes. You always need, no. So it's, if you have no negative eigenvalues, let's say all the eigenvalues are positive, then nothing from this side will be affecting that. So this sum, or let's say this sum will be empty and it doesn't contribute. Yeah, that's, in that case, well, you're right. But then let's imagine how this, we're always thinking maybe at the end of the day, we're going to be writing a code and that code will have that. So it's going to be hard to look at every single case and then just do, and then be kind of always looking at what happens at each point. So when you write a general one, of course, then you're going to write the general eigenvalues, and then if you're going to sum over all the positive, sum all the negative, and if there's no negative at that given point, then there is no sum. There's no contribution to the sum. So now let's use these two and just add them up. An average, because we're trying to compute what happens at this interface. So we have contributions from the left, contribution to the right. So let me write this. I think I need to move to the other side, because I'm not sure this will be captured here. So let me first take the average of these. And this will be this is a weird notation, but I'll explain in a second. So when you add these two, what we're saying, sorry, there was a minus sign mistake here. So when I add these two, what I'm saying, okay, we're going to have run over the sum that has the negative eigenvalues of that, and over the subtract of it those that have the positive eigenvalues of that. But now I can combine these in a slightly different way. It will be UI. So now, what we've done while doing so, sorry, this is wrong. This is a normalized eigenvalue. So we just combine these, and because we have minus the sign, we say, well, let's flip the sign and add over all eigenvalues. So this has a few things that are at our disposal. So this has a jump built in between the interface. And because we have that, then we have the characteristic decomposition. So what we formally have done is go to, if you want, the transform basis where everything is a one-dimensional problem, just an advection, and then we transform back to our original unknowns, which were the functions, the u. Yes. So in here, let me see. So in here I have a minus sign. So I'm going to put a plus sign. So here, let's imagine that lambda p. Now normalize it, it could be plus or minus 1. And so then if I multiply here by a negative sign, then I can just now change it to a plus sign and then put the absolute value here. And these were the details that kind of I was leaving aside yesterday when I just gave you the recipe for the road solver. This is now essentially tells you what you should do at every single interface to solve the problem a la row, which is an approximation to first order form. We include a few other kind of golden nuggets in there. One is we did a little bit better by extrapolating the values of the cell, because so far we have been thinking something like that. So we're just taking whatever value we have here and whatever value we have there. But remember, we had another twist where we said, well, just take the value there and extrapolate it to the surface by using a particular slope. So just to improve a little bit our equation. But we didn't overdo it. We only did it if the slope satisfies some particular properties. And we were always taking kind of the minimal slope, using the slope computed here, or the slope computed to the left, to use the smallest slope to extrapolate to the value here. So that improves a little bit, but it's just an approximation. The other thing I wanted to go back to is, remember yesterday I was being very cavalier, jumping back and forth between Q and Q and P. And the reason for that is because of something we need to discuss now. So first, let me just do an aside, and then we're going to go there. So we've been discussing all these problems with shocks and discontinuities, perhaps, rarefaction waves, and this type of equation. Let's say u comma t plus f of u comma x equal to 0, as if it were just its own entity. I never brought in the other type of equations, the one you discussed mainly with Sacha-Husa, that were not of this type. Were more like a type where we had a constant times the derivative of the function itself. It's one of those equations linearly degenerate, right? So I have, for the most part, ignored gravity altogether in our discussion. So what gives me the luxury of doing that? And that is actually a very nice property that applies to general relativity, applies to many sources of matter and energy that we care, but it's not necessarily completely generic. So let me tell you what is that property, and then do the caveat of something else. So let's just go back to general relativity and think of the equation that we're trying to solve, TAB. We're now going to discuss this TAB. But let me complete the aside. When we ask what are the equations of motion that are determined by this, well, roughly, what do we have in here? We have second derivatives of the metric. So I'm just being very schematic here. We have second derivatives of metric, and in the right-hand side, we have something. Let's imagine we have a perfect fluid. We're going to discuss more about that perfect fluid. But it means in the right-hand side, we have terms that have things like rho, density, pressure, velocity of the fluid, and if we talk about a perfect fluid, so for a perfect fluid, that's the right-hand side. The right-hand side involves rho, p, and u. Then we ask, what are the equations of motion for this rho, p, and u? And this is what we're going to discuss next. But roughly speaking, we're going to have things from the conservation of the stress energy tensor, which is a condition derived simply by, if you want, the Bianchi identities. The divergence of the Einstein tensor has to be 0, therefore the divergence of the stress energy tensor has to be 0. The equations of motion for those variables are determined by this. So it will give us derivative over fluid elements, let me call them, I don't know, curly f, equal to 0 or something. Of course, we have a covariant derivative. Because we have a covariant derivative, things in the right-hand side that involve g will have derivatives of g. Right? We're going to have Christoffel symbols. The Christoffel symbols have first derivative metric, and they will show up in here, in the right-hand side. If we, either in the left-hand side or the right-hand side, let's imagine me move them to the right-hand side. So now, at least formally, we see that the metric part is governed by a second derivative equation. That's the principal part. These are the higher derivatives in the system. coupled to the fluid, which comes completely undifferentiated. The fluid comes with, the equation of motion for the fluid comes with first derivative coupled to first order derivatives of the metric. So the coupling is not very severe. The highest derivative of the fluid, our first order, do not show up in the right-hand side of Einstein's equations with the source. The highest derivatives of the metric do not show up in the right-hand side of the fluid equation. So as a consequence, if we ask what is the principal part of the equations governing G and FR, they're completely uncoupled. Remember when we discussed, oh, why is that it's beautiful to have a sufficiently hyperbolic system? It's because I can ignore, by the most part, what the lower order terms are doing. They are not determining the general properties of perturbations over given solutions. They determine the particular solutions, but not the global properties, at least locally, of perturbations. Then we can consider, for all intents and purposes, if that's the case, the problem we're talking about, that they are by and large decoupled. So we can analyze the pathologies or the challenges of dealing with these equations independently of those dealing with these equations. And there's a reason why you had a full week with Sasha talking about this piece, and now we're concentrating on that piece. Is that clear? So the aside is that this need not be the case always. So you could be considering, for instance, a fluid here that might have viscosity. If it is viscous, there are other problems we need to worry about, but if we ignore those for a second, there are going to be derivatives of the fluid here. And so now the principal part of your term, of your equations of motion for the fluid, has first derivative, and so we'll have this first derivative of in the right-hand side here. But of course, if you have first derivatives here, you're also going to induce some second derivatives. And there is some very nasty business in relativistic hydrodynamics if you're dealing with viscous systems. We can, if anyone is interested. You might have other sources of energy. So Daniel was describing electrodynamics. So the Faraday tensor playing a role in here. But those are, we can make the same argument. The right-hand side, and I'll probably show this next lecture, the right-hand side for electrodynamics interactions involve the Faraday tensor. So it will be F's and F squared here, while the equation of motion of the Faraday tensor are D of F's, as Daniel described. So we have the same kind of nice separation. Because this has to do with the principle of equivalence of general relativity. So it's not that we're lucky and happens in that. But if you're talking about other theories of gravity, this observation might not apply. So let's keep that in mind. If you actually venture into the realm of non-GR theories, you need to think again, what is the source and what are the type of equations you're dealing with. So any questions on that? Sorry, not? Okay, let's move to relativistic hydro. So we're going to use this observation, we're going to continue using this observation, which we hadn't made till this point, to keep ignoring gravity for a while. And even we might even make a further shortcut to begin with and assume that we're dealing with equations of hydrodynamics for a relativistic fluid over flat spacetime. So we're going to assume that at least locally, the spacetime is flat. If not, then there are further complications that come up, but these are complications at the level of nuisance. They're not really fundamental because of the observation. They're essentially decoupled. So let's think of the first kind of matter source. It's a perfect fluid. It's unmagnetized. It's inviscid, so there is no viscosity that we have to worry about. So it's almost as nice as it can get. We're going to introduce a further simplification later on. But we can show that this stress-energy tensor can be written in the following form. So we have rho has to do with energy density. P is the pressure associated to that fluid. And eta is a Minkowski metric. As I said, we're just thinking that for the moment we're living on an otherwise flat spacetime. So rho is defined by the following relation. It's rho naught, 1 plus epsilon. We're going to introduce several different definitions that are related to each other. So rho has to do with the energy density content that an observer would measure. And that we want to kind of be mindful of two contributions. One is rho naught, which is a rest mass density. So if the fluid is completely at rest and you are an observer, come and measure its density, that's the contribution to the energy that it's providing. But now the fluid can be either moving, have kinetic energy, could be hot, then there is further sources of energy there. So that's why we're introducing this epsilon here. A related concept is that of enthalpy, which is 1 plus epsilon plus p over rho naught. It will come in handy in writing some of the equations. So enthalpy, if you remember in thermodynamics, is given by, in thermo, H is given by U plus PV, which is kind of in a sense telling us the ability of the system to produce mechanical work. But because we're in general relativity, we know that mass can also do work. We can change it into energy. So we add to this the mass. And once we introduce a specific density, the specific enthalpy, and say we divide through by the mass, then you end up with things like this. So 1 is the equivalent to this contribution. U is given by the energy, the extra stuff that is not the mass, and P over rho is essentially given by that. So rho 0 sometimes is also written as n times m, where n is the number of particles that we think are describing our fluid, and mass is the mass per particle, the rest mass of the particles. So we have, if we count, we have as unknowns rho, p, rho 0, epsilon p, u. We have to also imagine how many equations we have, even if we can determine them all. So we have a conservation of particle number. We're going to write as rho UA, rho 0 UA, equal to 0. So this is just a sense that we're not creating or destroying particles at will. This we might have to worry about at some point, depending on if we have reactions where maybe some particles come, interact, and produce photons. So this gets relaxed. And in some of the studies that Daniel will show, perhaps in his colloquium, one is introducing further physics because of that. But we're keeping as simple as we can at the moment. Then we have this other equation, which is the conservation of stress energy tensor, which I said is related as well to the conservation of the Bianchi identities, the divergence of the Einstein tensor being 0. So these equations, we have 4 equations here. I have 1 equation there. We have 5. And I counted here as 1, 2, 3, in principle 4, that's 7. But we have constraints. We have UA is -1. So we have 1 constraint there. And we have that the pressure should be given by some equation of state. So now I have 5 equations for 5 unknowns, because I have 2 constraints. Again, if we're thinking of a more complex, like Daniel was showing, that the composition, the electron fraction composition, or how much neutrons and electrons might be there in your fluid, you might have these also depending on that fraction, and further equations need to be added. So now, suppose we're an observer. What is the density that an observer would measure? So rho, let's say ADM, is defined to be simply TAB. And now I'm going to think of some observer. Who is that observer? Let's imagine it's the observer is normal to the hypersurfaces. Daniel was calling it K just a few minutes ago. That's TAB and A and B. So N in your foliation is a normal to that foliation, which need not be normal, which will not be parallel. So let's say normal is not. So UA need, sorry, the other way. NA need not be parallel to UA. So if we use this in the definition, we can rewrite this in the following way. So the energy density that an observer will measure will be given by several terms. H is the enthalpy that we define there. Rho 0, we have it there. P is the pressure. I still need to tell you what this odd with W is. And W is nothing but, it's precisely this value that you get if U and N are not parallel to each other, or at least if they are not, if U is not normalized, and they are not parallel to each other. So this, we actually measure what it is with respect to the observer that has an N. It's nothing but the Lorentz factor measured by that observer. Sorry, I'm going to put a minus sign here. Yeah, so we can look at that explicitly. Suppose we have that. Let's imagine that we have in here coordinates where this one is 1, 0, 0, 0. And now we have the velocity, let's say UA. So let's imagine this is normalized. This is whatever it has to be, which is also normalized, but it's not parallel to N. So now I can do that. The projection of U along N is something, and orthogonal to it is something else. So the one that is the projection of U orthogonal to N is the velocity that an observer will find times the Lorentz factor, and then U dot N will be the Lorentz factor. So let's do a little bit more here. So rho 0 H, let's use the expression for H. So rho 0 times H will give us several contributions here. So there will be omega square times rho 0 times rho 0 epsilon plus P minus P. So let's see, yes? Yeah, so let's take it, imagine that N is, it can be any observer. So here I'm just chose it to be, say, orthogonal to that hypersurface, but it not be. As long as it's a time-like vector that is normalized, we can always refer to it. Oh, good. We're going to leave it free, because it need not be the case that we're going to turn the equations in terms with respect to N. We can, at the end of the day, we can have three different kind of coordinate systems if you want. One which goes along the U field, that's usually called a Lagrangian observer. So one that is moving with the flow, that you're just moving at the same speed of the flow. For you, the flow is completely at rest, and you can have a coordinate system associated to that one. You can have another one that is associated to the normal to the hypersurface. And then you can have another one that you choose by the sake of whatever you think is the best set of coordinates to use. And this you saw, I think, with Sasha. So let's imagine now this is the normal, NA. But we can choose our label such that, say, this point in here, which may have labels xi. If I go along the normals, then might have xi plus some delta x. and somewhere here is the label we chose, or the point that we choose to have the same labels of that one. And the relationship between going normal and going to the side and given the same labels is given by the lapse and the shift. So then this vector NA, in terms of those, can be written as 1 over alpha dt A minus beta A, let's say. And so, because we want to have at our disposal the freedom of coordinates, which need not be attached to the physical behavior of the fluid, nor attached to the normal to the hypersurface, because it might be bad, depending on what the hypersurfaces are doing, we typically will choose to use dt to label all our time, the rate of change of all our main variables. So we're going to, at the end of the day, write the equation of motion with respect to this dt. Of course, with the appropriate choice, when we did that for several reasons, but one particular one is with the appropriate choice of lapse and shift, we can always adjust things so that if I take lapse 1, shift 0, now my coordinates align to the normal to the foliation. And if I choose it to be something else, we can choose it to be such that they follow the U trajectories. So that's one of the added bonus of choosing the lapse and shift at first arbitrarily, and then you change depending on what particular application you're thinking about. So imagine we choose such a frame where this factor, this omega, happens to be 1. So then as a result, this energy density that observer will measure is nothing but ρ0 plus ρ0 epsilon, which is the energy density that you'll measure if you're going with a fluid. You measure its rest mass, and however extra energy you may have due to the fluid being hot, for instance. So now let's think of the equations of motion. And he said, well, in principle, we want these equations, but we're taking, for the time being, the assumption that the metric is flat. And so then these equations are simplified a little bit to the following. So no Christoffel symbols, we got rid of them. So now what we want to do is analyze those equations. But we want to do it knowing full well that because of the structure of the equations we have, and this will be obvious, for instance, if we take the divergence of the TAB, so if we think about this one, it's going to be obvious that some terms will involve U derivatives of U, right? Simply because we're taking a derivative here. But because we have U times derivative of U, we're going to have things that look like now the Burger's equations, things that the terms are not going to be linearly degenerate, the equations are not going to be linearly degenerate, they're going to be truly nonlinear. So because of that, and because the intuition we have that fluids will lead to shocks, we want to keep in mind everything we've discussed with respect to kind of this type of equations where the eigenvalues depend on the solution itself. To be mindful, we have to be mindful of that to create or to come up with a particular strategy to push forward and then understand how to write these equations. So let's start with this one. This is the easiest one. This one equal to 0. Now remember, we said, for several reasons, we wanted to write things in conservation form. Thanks to that, we can write things as, or we can imagine things as averaging cells and solving Riemann problems in interfaces. So this will translate into, let's say, the following. So it's rho ut plus rho ui. Now I chose my coordinate system so that n is special, at least for the time being. So I can rewrite this in the following way. Or let me just say ut, let's say if we choose NA so that such that NA is just 1, 0, 0, 0, this is picking ut for us. Right? But ut is W, is a Lorentz factor. So I can rewrite this in the following way. Sorry, and this is rho 0, I forgot the rho 0. So let me just say two more things. So we define that one, and let me define Vi as Ui divided by U0. So what am I doing here? And I haven't told you, oh, I'm forgetting one more thing. So I define so let's define D as rho 0 times omega, or this W. So notice this one and that one I got up to a sign, but we're going to carry the sign through. There's a minus sign overall. Up to a sign, rho 0 ut is W, then that's what we're defining as D. So we're creating a new variable called D that has a combination of rho times U. Here, I have rho times Ui. I can multiply it by ut divided by ut. The ut combined with the rho gives me back D. And the R1 is the one I'm used in this definition for the velocity. So it's just a relabeling of variables in a convenient way, but we're beginning to go into trying to define or recognizing that maybe combination of variables will be what we want to keep writing things in conservation form. This particular question is not that complicated. The next one will be. So let me just describe the following one and then make the connection. So now what we want to do is write this equation, which, because we're in flat space, we're doing this. We have some freedom here, because if that equation is satisfied, so is this equation. Doesn't look like we're doing much by raising or lowering an index, but that actually translates into what we're going to end up for expressions of new variables. So let me just first define the following. So this is just a definition. So I'm taking TAB as a combination of some vector multiplying the vector U, kind of normalizing by the Lorentz factor, and a contribution of the pressure. So this, if you want, it's just a definition of this S with respect to T. The reason we're doing that is with that definition, we can replace that in here, and then the equation becomes the following way. So we introduce a new variable related to our stress energy tensor this way. We haven't completed everything because I'm taking I, the component on the orthogonal to the vector n. We still have to resolve on one last equation, but let's look at this equation for a second. So you have the time derivative of a variable s. If we look at what the variable s is going to be a combination of u and p and this variable s, and then if we work out what that s turns out to be, is the following. So S is a highly non-trivial variable defined with respect to all our variables here, our original variables. In terms of that one, then we can write this equation, and this equation is the rate of change of S notice it's the derivative of some flux that knows, so it's a vectorial derivative of some flux, plus some piece. If we didn't have this piece, this would be perfectly good as far as a conservation form. This is what we'll be discussing again and again. So this is how the momenta of your fluid, or our fluid, is changing with respect to flux and respect of the gradient of P that is related to the effective force that gradients of pressure introduce. And here we're already understanding or seeing what the problem is going to be. Suppose we have a recipe to iterate these equations. We're going to have S from here and D from there. Knowing S and D still doesn't tell us what the original equations or what the original variables were. Our original variables, just to remember or remind you, is rho 0, epsilon, let's say, and UI, or let me just call it VI. And then we're going to introduce a name for it. We're going to call them primitive variables. So these are the variables we use to understand the physical properties of our system. But these are not the convenient variables to carry out the integration. The variables that will be convenient for that, we're going to call them conservative variables, because they lead us to write a system of equations in conservative form. And it will be this D, this S, and I still have to give one, let me call it E. And so we're going to be going back and forth between these ones, which will be the ones we use to integrate the equations, and these ones, which are the ones that we have naturally physical intuition about in some sense, and the ones that appear in the right-hand side of Einstein's equations. So let me just give you the last equation. Let me, well, here. Oops. Because we're introducing variables, we can introduce variables as long as we have a complete set of variables from which formally we can recover the initial ones. The only thing we care is our variables to satisfy a conservation law form that we can work with. So we had that density that we call the ADM. Let us define the following. Some variable E, which is the one I'm going to use there, as this rho ADM minus rho 0 W, which is what we call this D. So what we're doing here is take the full energy density that our observer will measure and subtract from it the rest mass energy density. So we're just taking a piece out of it. The reason for that is that sometimes on the numerical level, this will happen often, this term is just so much larger than that, or the extra piece from this that is not the rest mass energy density, that it's just too hidden in the noise. It's too hidden in the numerical error. So we clean that out from that variable, from this variable, subtracting it out, and whatever is left is kind of the kinetic part of the contribution to energy density. So now we need an evolution equation for this variable, and we can do it from here. So I now choose the 0 component. That's the only one I haven't used so far. These using the definitions that we have introduced so far. So we can now take the time derivative through. Write this in respect to time and space derivative. This gives us the following. And then a further step to relate this S naught to this epsilon, because S naught, let's say, this relation is satisfied. So once we replace that in here, and we use the evolution equation we had for D, then we can combine everything into the following equation. So we now have, let me just circle this. So those are our variables. So those are our evolution equations. By and large, with that exception, they're all conservation law form. And they are the ones that we would use to iterate the equations of motion. And again, so now is where we hopefully pays off what we discussed about the simple equations before. We would have a set of unknowns given by D, S and epsilon. Our equations of motions are truly nonlinear. For instance, in here I have S and I have V. V depends on S, so we have nonlinearities here, same thing here and over there. And so we think we have gained a lot by going through these variables, because we have this in conservation form and allows us to use all the techniques to deal with these discontinuities and this funny or interesting kind of behavior that fluids will give rise to. But there is a price to pay. The price to pay is these new variables that we have introduced, which are related to each other in a nonlinear way. So what we have to add to our construction is a way to go from the original variables to these ones. That's trivial. It was all algebraic. But then we have to go from here to there, and that's going to be nonlinear. And you'll be surprised how much time and effort is being spent in this. Because typically you could end up finding not good solutions, divergences, all sort of pathologies. In some sense, we move them from the original complication of equations to this step here. I mean, already, what was it, last year, we had a workshop at Perimeter, which even had a very lame term. It was conservative to primitive workshop or something. It was, because this gets to be so complicated. Not at this level. This is a very sufficiently simple system of, or physical model that this is not that complicated. But if you complexify it by adding magnetic fields or non-trivial equation of state, this becomes highly non-trivial. So what else, what other pathology have we gotten ourselves into by this choice? The other choice, so let's imagine you have just evolved the system. You have D, S, and epsilon somehow, and you want to go back and obtain the primitives. So somewhere, you're going to be going, for instance, from D to rho 0. That's the simplest one, because after all, it was just, what was D? Somewhere there. See? So this is as simple as it can get. So now imagine what happens in a star. So you have a star here, and outside is vacuum. So you have rho here, and rho equals 0 there. So how do you know in here that you're in the vacuum regime and the solution should have density equal to 0? You don't know. So this is, suppose you have this star and the star is doing this. So if the star is put, you could kind of understand where the surface is and perhaps realize that this should be vacuum. But generically, you don't know. In fact, you saw from the simulations, you could have ejecta. You could have material that has been outstripped from the star. So something that had a low enough density may or may not be vacuum. So as a result, dividing by 0 is a very bad idea. That's always the case. And so typical simulations will actually never have density equal to 0 at the outside. You'll have density as low as possible. So you embed the whole system you're dealing with in an atmosphere. That's how it's called. So let me give you a very worrisome number. The typical codes, the ones that Daniel showed, the ones that I show, the ones that you'll see anywhere talking about when they're describing, like, say, neutron star, the collision of neutron stars, the codes have been very carefully written. All effort has been put in there to try and maximize this kind of contrast between what you would call the star and what you would call the outside of a star. So typically, there is of order maybe 10 orders of magnitude, 9, 10 orders of magnitude between the density at the center of a star and the density of what you would say that's outside of the star. That sounds pretty good. You're resolving 10 orders of magnitude, 10 orders of scale between here and there. But then you ask yourself the question, what is the density of a white dwarf? The density of a white dwarf is not too different from 10 to the minus 10 times the density of a neutron star. So the collisions we were showing were not the collision of two stars out there in vacuum. There were two stars colliding inside another star that it was a white dwarf. That's not a big deal, because once you're talking about 10 to the 10 times on the bulk motions of the star, that's, by and large, it's nothing. The fluff that is outside is doing nothing. But once you start talking about the outstrip material, this ejecta is going out, and Daniel and collaborators are very hard at work trying to predict light curves. This little bit of material that is going out is just fighting through this very dense fog. And so for very long simulations, this could be an issue. And so this is something that a lot of people are working on. Depending on what particular stage you are, there are different approximations you can make. But this is a question that it's in the back of everyone's mind trying to improve. Because there are other techniques. Everything we've discussed so far here in these finite volumes, think or consider this, the fluid is described by fields. There are other techniques out there, and maybe some of you have heard of these. One is kind of common under this name, smoothed particle hydrodynamics. There you're not considering your fluid as a field, but it's a collection of particles, and you're following each one of those particles. These codes are amazingly good at doing many interesting things. Their convergence properties are not as great. They converge as the number of particles, as the square root of the number of particles, and so you get very cool pictures, you get very nice qualitative answers from them generically. How good the qualitative answers are depends on the particular problem you're dealing with and how many particles are you able to put in your simulation. So, but I don't want to give the impression that there is not a lot of value here. In particular, to follow some of this material, people are looking into these hybrid models to then follow this ejecta that is going out using that, and then bypassing all this extra, if you want, baggage that you have to get with when dealing with this type of equations and having to face a problem that the physical difficulties in following these kind of solutions. So I think I'm going to stop here. So tomorrow or Thursday, I'll very quickly just kind of flash how do you go from here into the larger problem of general relativity, how you put this in a general relativity context. Many things that we're going to be discussing with are, as I said, fluff. They are not that important. For instance, one of the things we're missing here is all the Christoffel symbols. Where did they go? All the volume elements, where did they go? By and large, it will not change the qualitative pictures that we discussed today. But at the bottom line, what we're going to be doing at the end of the day is just trying to write the equations in conservative form. We're going to pay all price that we need to pay to get there. And in particular, the worst price is this one, having to have a good recipe to go from the conservative to primitives, and dealing with this atmosphere. Notice that we need the conservative primitive in many steps. So in here, if I want to evaluate this flux, I have the velocity. I see it explicitly. I need to get it, because that's not the variable I'm iterating. I have the pressure, the same thing, and I have the velocity. So this is this conservative to primitive inversion back and forth becomes an integral part of your scheme as a whole. So beyond this, all these high resolution shock capture methods that do a great job, this is a crucial ingredient. Sorry. Any questions? No? Yeah. I mean, to some degree, it doesn't overly complicate it, but it makes it more challenging just because the velocities might be higher. So if I have a fluid here that has kind of small velocities and I don't have any curvature around to accelerate particles, then my conservative scheme maybe doesn't work really hard. But if you have now a black hole and then this particle that is moving at very small velocities over there, now it's moving at very high velocities. Now your scheme has to be sufficiently general to deal with that and to deal with this. And so these things actually do come and play a role. I mean, it's so funny. People don't do it these days, but it used to be. And it's not that the problem has significantly changed. It's just people got tired of seeing the same plots. They would plot you, the solution is looking like this, and then sometimes you will see another plot that will present is a number of failures in here versus time. So the code is failing at points all the time. And as long as it stays a small number, then things were going well. So because what typically happens is you may have places where truly, because of discretization errors, let me give you a stupid example. Suppose you want to go from W, I mean, we can do this exercise tomorrow. Suppose you want to go from W to V or something. So at some point, you're computing things like 1 minus V squared. So you're computing V. And you are in a place where the fluid is at rest. Okay, that's fine, no problem. Now imagine you go very close to the fluid is almost moving at the speed of light, which could very well happen. So analytically, you know that this one is bounded by 1, and the worst can happen is this is 0. Numerically, that 1 can be 1.00001, which is ridiculous, it's not physical, but now 1 minus that number will be negative, and you're trying to take the square root of the negative number. So then you say, well, no, of course I know it's bad. I put a flag in my code, and if I'm going to evaluate that, I'm going to say, okay, that I cannot do. I'm not going to let it take the square root of a negative number. But then what do? You shouldn't take the negative number, but you still need a value at that point. And so then different codes will do different things. We'll look at the neighboring points. So I'm now telling all the dirty little secrets, and different people have different secrets. So now you look at that point and say, well, this, I don't know the solution. I cannot evaluate it because something unphysical is going on. But I was able to get all the points around me. So maybe I'll interpolate. Or maybe you'll see that for the type of equation state you're dealing with, you cannot get a physical solution. So then you go to a different equation state that is slightly more robust or something, so you're getting a bad solution. Because on average, things get to work fine, and then you try this through numerical test. Because after all, this one was maybe 1 plus error, and the error goes like h squared, and eventually that one goes to 0 and everything is fine. So eventually that point that was misbehaving now doesn't misbehave anymore. But this comes and bites you in many ways. You could be absolutely super careful, and then your code will be terribly slow. You could be very cavalier, and then you have too many failures, and then the solution becomes unphysical. It is, unfortunately, so I started saying the other day that you need to know analytically as much as you know, and then those guide how we go through in the most robust manner. When it comes down to here, I think there is a lot more to be understood or developed. So this workshop, there are very good ideas. These ideas are always pushing things in the right way. But I think because of these things, because of the truncation error just playing a role, sometimes you're fighting with the way the error behaves and how it impacts this transformation. Curse the day that I went into fluids because of these kind of things. Of course, they are more fun. I like to see what they are doing, but I have to deal with these things. Any other questions? So if not, one thing we're going to do is suggest a couple of exercises. So maybe I'll tell you what exercise I was going to suggest, and this is very simple. In fact, I show you already what the behavior is. And then Daniel is going to suggest some other one. And then you just work on those, work at your pace. We're going to be here the rest of the week. So ask questions as you need. Pick whichever one you like. And if there is one that you think you can do it, you have a good feeling that you can do it, then don't do that, because then you can do it. And then try the other one that you don't, it might be more complicated. So the one I was going to suggest is just take the Berger equation and implement the row solver, implement the standard differentiation kind of with the techniques that that Sasha Husa described to you for both this equation and the Q, the one where you wrote it this way. And recover the kind of things that we discussed. I don't know what you code in. You all have, or those of you that have laptops. These problems are sufficiently simple and self-contained that you could do them with, if you're a hard coder, you would C, Fortran, Python, but you can also use Mathematica, Maple, anything that allows you to write down a vector and update that vector in time. Try it, and if you don't know by now, make sure you ask us. Any one of us can help you out. Because at least if you know that, if there's one message that we are trying to give you in this workshop, is that if you know how to deal with this equation, and you know how to deal with this equation, you pretty much know how to do generativity with hydrodynamics. I mean, I know that I just take a huge leap, but if you actually do this, the building blocks of this is what is used intrinsically in every single code out there. So give that a try. So you want to give your exercise? Of course, if you're quick and you implement this relatively quick, let me know, because immediately I can suggest something to do with hydrodynamics. So and this is what I'll describe tomorrow, but or Thursday. But start with this one. Daniel?
Okay, so here's another numerical project, another suggestion, just in case you want to try something numerical. And so one interesting project could be to actually implement the very basic kilonova model that we discussed yesterday. So if you go to the webpage of the lectures, these lecture notes will be linked there, and you can go there. And essentially, you can pick any sort of programming language of your choice. So as Louis said, it can be Python, it can be Mathematica, any sort of language where you can sort of write some scripts that can do some time evolution of sort of some simple equations. In this case, what you need to do is essentially just evolve an ordinary differential equation in the end. So you can essentially just go through these equations and just implement the main expressions that are given there, and just put sort of everything together, and then in the end just evolve the main equation. So I can put you to those. So you would need to implement this profile here. Then what you're gonna do in the end is evolve exactly this equation here, the evolution of the internal energy. So you need to provide specific definitions of these source and sink terms here, of the radiative luminosity, the heating rate, and the PDV work. So you just need to go through the script, find the specific expressions that we derived for these terms, put them in there, and then just evolve the internal energy as a function of time. You would integrate this equation. You can just use, if you want, just a ready-to-go ODE. So you don't need to do any work on that if you want. Just implement. So these are the expressions for the luminosity, for example. Well, I have the mouse here. So this one for the luminosity, and then you go and find